When people hear the phrase cosmic expansion, it sounds like something pushing galaxies apart. Gravity sounds like the opposite, a force that pulls things together. So it is natural to ask, what is gravity doing while the universe expands? The modern answer is subtle. Gravity is not just a force inside space. In general relativity, gravity is the behavior of space-time itself. Expansion is also a behavior of space-time. Once you accept that, the question becomes sharper. Which parts of gravity slow expansion? Which parts speed it up? And how do we know? I start with the basic observation. Distant galaxies show redshift. Their light is stretched to longer wavelengths. The simplest interpretation is that space between us and them has expanded while the light was in flight. This is not the same as galaxies flying through space like shrapnel. On the largest scales, the pattern is closer to a changing scale factor, a T, that multiplies cosmic distances. We measure how that scale factor changes by combining redshifts with distance indicators. The key point is that expansion is not guessed, it is mapped. General relativity tells us how expansion responds to what the universe contains. In a homogeneous and isotropic universe, the expansion rate ht follows the Friedmann equations. In plain language, the rate depends on the energy density in matter, radiation, and any vacuum-like component, and it depends on spatial curvature. Gravity enters through the fact that energy and pressure curve spacetime. That curvature dictates how the scale factor evolves. If the universe contained only normal matter, then gravity would slow expansion over time. Matter has positive energy density and negligible pressure, so it gravitationally attracts. In the Friedmann picture, matter makes the expansion decelerate. You can think of it like throwing a ball upward. It keeps moving up, but gravity reduces its speed. The universe can keep expanding forever and still be decelerating on the density. Or it can eventually stop and recollapse if the density is high enough. That was a serious possibility for decades. But matter in our universe is not just the atoms we can see. Most of the gravitating matter is dark matter. We infer this from multiple lines of evidence that agree with each other. Galaxy rotation curves show stars orbiting too fast in the outskirts to be held by visible mass alone. Clusters of galaxies, through the motions of their member galaxies and the temperature of their hot gas, require much more mass than we can see. Gravitational lensing, the bending of light by mass, maps that extra mass directly. In colliding clusters, we see the lensing mass separated from the hot gas, which is where most of the ordinary matter sits. That separation is hard to explain without a dominant collisionless component. Dark matter adds gravity, so it should add deceleration to the cosmic expansion. Here is the twist. When we actually measure the expansion history, we find that the expansion is not just continuing, it is accelerating today. That means the scale factor is speeding up, not slowing down. In the Friedmann equations, acceleration requires a component with sufficiently negative pressure. In general relativity, pressure gravitates. Positive pressure adds to gravitational attraction. Negative pressure can act like gravitational repulsion on cosmic scales. This is where dark energy enters. The cleanest evidence for acceleration came from type 1a supernova. These are exploding white dwarfs with a fairly uniform peak brightness after calibration. They act as standardizable candles. By comparing their observed brightness to their redshift, we reconstruct a distance redshift relation. In the late 1990s, teams found that distant supernovae were dimmer than expected in a decelerating universe. The simplest interpretation is that the universe has expanded more than it would have if matter were the only driver. More expansion during the light travel time makes the supernova appear farther away. That is the signature of acceleration. Supernovae are not the only evidence. The cosmic microwave background, the afterglow of the hot early universe, carries a precise imprint of the geometry and contents of the cosmos. The angular scale of acoustic peaks tells us that the large-scale geometry is close to flat. But if the universe is flat, then the total energy density must be very close to a critical value. When we add up the matter density inferred from galaxy clustering and lensing, we come up short. Something else must fill the budget. That missing component behaves like dark energy. Then there is baryon acoustic oscillations, a standard ruler imprinted in the distribution of galaxies. In the early universe, sound waves moved through the plasma. When atoms formed and photons decoupled, those waves froze into a preferred scale. We see that scale today in galaxy surveys, measuring it across redshift maps the expansion history. BAO results line up with supernovae and the microwave background. Together they point to a universe with about 1/3 matter and about 2/3 dark energy, with dark energy close to a cosmological constant. So where is gravity in this story? It is everywhere. Gravity governs the expansion through the Friedmann equations. Gravity also builds structure. Small density fluctuations in the early universe grow over time because gravity pulls matter into overdense regions. Dark matter is crucial here. It starts clumping early because it does not couple to radiation the way ordinary matter did. That early clumping forms gravitational wells. After recombination, ordinary matter falls into those wells. That is how we get the cosmic web of filaments, clusters, and voids. This leads to a helpful thought experiment. Imagine a universe with the same initial fluctuations, but no dark energy. Gravity from matter would keep slowing the expansion. Structures would have more time to grow. Clusters would become more massive. Voids would empty out more. Now turn on dark energy that behaves like a cosmological constant. As the universe expands, the matter density drops because it gets diluted. But the energy density of a cosmological constant stays constant per unit volume of space. Eventually it dominates. When it dominates, the expansion accelerates. That faster expansion makes it harder for gravity to pull new matter into bound structures. Growth of large-scale structure slows down. In that sense, dark energy changes gravity's outcome without changing the local law of gravity. It changes the background spacetime in which gravity operates. It is important to separate two regimes. On small scales like the solar system, gravity is well described by general relativity with tiny corrections. Cosmic expansion is negligible there. Bound systems do not expand with the universe. The Milky Way does not get stretched by the Hubble flow, neither does the solar system. On large scales, where matter is smoothly distributed on average, expansion is the dominant behavior. Gravity still acts, but it acts through the average energy content and through the growth of perturbations. Now I want to address a common confusion. People sometimes ask, if gravity is attractive, how can it cause expansion at all? The answer is that expansion is not caused by gravity in the way a rocket causes motion. Expansion is a solution of the equations for spacetime, given initial conditions. Gravity from matter tends to slow that expansion. Dark energy, if it is a cosmological constant or something similar, tends to accelerate it. Both effects are gravity because both come from how energy and pressure curve spacetime. What do we actually mean by dark energy? The simplest model is the cosmological constant, lambda. In the equations, it behaves like a constant energy density of the vacuum with pressure P equal to minus rho times c squared. That negative pressure leads to acceleration. Observationally, current data are consistent with an equation of state parameter W close to -1. But we do not know what lambda is microscopically. If it is vacuum energy from quantum fields, naive calculations give a value vastly larger than observed. That mismatch is the cosmological constant problem. It is one of the biggest unsolved problems in fundamental physics. There are alternatives. Dark energy could be a dynamical field that changes slowly over time, often called quintessence. Or the acceleration could signal that general relativity needs modification on very large scales. Scientists test these ideas by measuring not just the expansion history, but also the growth of structure. In general relativity, once you specify the expansion history, the growth rate is largely fixed. Modified gravity models often predict a different relation between expansion and growth. So we compare weak lensing maps, redshift space distortions, cluster counts, and the microwave background lensing signal to see if gravity behaves as expected. So far, general relativity passes these tests at impressive precision. The simplest lambda CDM model, with cold dark matter and a cosmological constant, fits a huge range of data with a small set of parameters. At the same time, there are tensions. The most discussed is the Hubble tension, a mismatch between the expansion rate measured locally using distance ladders and the value inferred from the early universe using the microwave background within lambda CDM. There is also the S8 tension involving the amplitude of matter clustering. These could be systematics or they could be hints of new physics. At the moment, the community is cautious. The evidence is not yet decisive. Gravity also determines the universe's fate. If dark energy is truly a cosmological constant, acceleration continues forever. Distant galaxies outside our local group will eventually recede so fast that their light can no longer reach us. The observable universe becomes emptier over time. Structure formation effectively freezes out. Locally bound systems remain bound. The long-term future is a cold, dilute cosmos with isolated island galaxies. If dark energy changes with time, the fate can differ. If it weakens, acceleration could slow, and matter could regain influence.